Hi everyone, my name is Matthew Spencer and I'm here today to talk to you about replacing transistors with mechanical switches. Upon hearing this, you might rightly think, why on earth would you do that? I'm going to reply by taking a sort of roundabout route through history and pointing out that there's some poetry to this. The first computers were in fact mechanical. This is a picture of Babbage's difference engine, which when powered by a hand crank could solve fifth-order polynomials. If you fast forward 100 years, you get to ENIAC, which was the first fully digital electronic computer. It weighed 20 tons, consumed 150 kilowatts of power, and performed a blazing 5 kiloops per second of floating point operations. Now, the difference between these two computers points out a tension in computer design that's been around since the 1840s, which is between high power and high performance and lower power and lower performance. Fortunately, we broke some of the design trade-offs in a pretty significant way since the 70s, but this tension actually resurfaced in a very significant way around 2000. This plot is a prediction of how computer power would increase from 2000 to 2010, and you'll notice people expected power would increase a lot. This obviously didn't happen, as indicated by some of the annotations on the slide. We don't have nuclear reactors in our laptops. The question is how this happened. Ben has actually prepared us very well for this. The idea is that transistors have a property called their threshold voltage. And if you adjust their threshold voltage properly, you can trade off between two kinds of energy that are dissipated in them. A very necessary energy called dynamic energy, which has to do with running the computer, and wasted energy called leakage energy. By setting the threshold voltage properly, you can actually find a minimum between them and make them operate perfectly. This is actually what happened between 2000 and 2010 and is why we have many cores in our computers right now. I'll talk through that based on the cartoon on the right of the slide. The idea is that if you were operating at the 1x point in that cartoon, you're consuming lots of dynamic energy above the optimum. However, you can slow yourself down in order to save energy, and then stick two computers next to each other in order to recover your performance, and let the software engineers figure out what to do with two computers. You can do that again in this cartoon, going from 2x to 4x parallelism in order to save energy, but once your core is at that optimum point, running it slower won't save you any energy. And so as a result, you hit this ceiling on parallelism, which limits our ability to improve computing performance going forward. Now, at this point, my group takes a turn sharply into left field and says, the problem here is the transistor. If we can replace that with something that doesn't have this wasted leakage energy, then we can continue improving computing performance by scaling our voltage forever until we hit some other physical limit. And what's significant about this idea is that we've succeeded in building it. This is a cartoon of the device that we built. The idea is you have a piece of metal hanging out in the air suspended by a spring. When you put a voltage on that piece of metal, it's pulled towards the surface, and decorations on the bottom will connect different points on your chip. The other significant thing is, after we built it, we measured it and found out that it has immeasurably low leakage. As near as we can tell, it has none. So this means that we can replace the drawing from the previous slide with the drawing in the bottom corner of this one, where there's no leakage energy and we can just keep scaling forever. Now, does this mean it's a good idea? Not necessarily. Mechanical devices are big, and they're slow compared to electrons. So there's a chance that we'd get very energy efficient, terribly performing computers if we tried to use these. However, we've done a lot of very interesting work with circuit design in order to mitigate that problem. In particular, by changing our design style from stacking series of gates next to each other to making very large distributed gates where all of the inputs hit at the same time and therefore all of the mechanical delay is incurred at the same time, we can improve both our performance and our device count to save power, energy, and delay. This is even more significant because we've built some of these things. We've demonstrated that it's possible to get the functionality that we've been talking about, and we've done a lot of extensive simulations showing that we can improve our performance. Our original test case was an adder, which we demonstrated in 2010, and simulations show that you can get 10x improvement over the absolute best a transistor could do in terms of energy for only a 10x delay penalty. We've also built a microprocessor, and there's other stuff coming in the future, including optimized memory structures made out of these. Thank you.